We have drawn the distinction between ionic and covalent bonding, where ionic bonding is the interaction of oppositely charged ions, and covalent bonding is the sharing of electron pairs between neutral atoms. But is there something in between? In fact, a better representation is that the previous descriptions of ionic bonding and covalent bonding are at two ends of a continuum, and in between we can describe something that we can call a polar bond. Let's start by thinking about two bonds, an HH bond and an HCl bond. The HH bond is one that we might call completely covalent. The two electrons in the bond are equally shared. But in HCl, the electrons are not evenly shared. Recall that electronegativity is the ability to attract electrons in a covalent bond. Chlorine has a larger electronegativity than hydrogen, so the electrons will not be equally shared, but attracted toward the chlorine. This is sometimes indicated by an arrow, pointing the way in which the electrons are pulled. The arrow has a small tick mark at the other end that looks like as if a plus sign may have been attached to the arrow. In fact, if the electrons are pulled toward chlorine, the chlorine atom should pick up a little bit of a negative charge, and the hydrogen would have a little bit of a positive charge. These partial charges are sometimes indicated by these symbols, where the Greek lowercase delta is a symbol for partial, much like it is in partial derivatives, if you've gone that far in calculus. We would say that this is a bond dipole. Much like the Earth is a magnetic dipole with a north and south pole, this bond has two poles, in this case a positive and a negative pole. We'll also call this a polar covalent bond, since electrons are still being shared, but shared unequally. Thus, the bond is polar. Polar bonds are due to a difference in the electronegativity, or delta En, between two atoms that are sharing electrons. If the difference is small, the two atoms are relatively equal in their ability to attract electrons, so the polarity will be rather slight. The partial charges will only be a small fraction of a charge. If the delta En is larger, the degree to which the electrons are pulled to one end is greater, and the bond is more polar. Thus, we can rank bonds in their degree of polarity from less polar to more polar. Here are the p-block elements in the third row of the periodic table. We know electronegativities increase going to the right, although argon, with the exception of a few unstable compounds, is not involved in covalent bonding. If the electronegativities of the two atoms in a covalent bond are identical, we would expect the bond to be nonpolar or completely covalent, with no positive or negative end. An example would be the Cl-Cl bond. Elements next to one another have similar but not equal electronegativities, so we would expect the SiP bond and the SCl bond to be slightly polar. SiS would be more polar, and AlCl would be the most polar bond that could be formed from these elements. As bonds get more polar, the electrons are less equally shared, so they get more like ionic bonds and less like purely covalent bonds. Here is figure 5.5 from the textbook. On the y-axis is the percent ionic character. On the x-axis is the difference in electronegativity. The plot shows that as the difference in electronegativity gets greater, bonds become more ionic and thus less covalent. The plot might suggest that there is a border between covalent and ionic bonds at an electronegativity difference of about 1.7, but we shouldn't draw that conclusion. Rather than thinking about a border, we should realize that bonds that have small electronegativity differences are mostly covalent, with a bit of ionic character. Bonds with a large difference in electronegativity are mostly ionic, but still have a bit of covalent character. If we look at it this way, our model of the ionic bond as the interaction of spherical charges probably isn't completely correct, but we'll still use it. The other reason not to consider a border between covalent and ionic, but rather a continuum, is that there are a few examples here that would appear to be on the wrong side. For example, the bond between the nonmetals hydrogen and fluorine would appear to be slightly more ionic than covalent. The three bonds highlighted in red are between metals and nonmetals, yet they appear to be more covalent than ionic. Do we need to remember these exceptions? No. We are going to keep our rule of thumb. If we have a metal and a nonmetal, we will still consider it an ionic bond, even though there may be a considerable amount of sharing. If we have two nonmetals, we will still consider it a covalent bond, even though there may be significant polarity. We just have to be aware that this distinction is not 100% accurate, and that all bonds lie somewhere on the continuum.